think we'll move on to the next speaker now. So I'm hopeful that the next speaker, Jessica Tierney, who's from the Department of Geosciences at the University of Arizona in Tucson, will come on. And Jessica has recently been awarded one of the prestigious fellowships from NSF in the States. And she's going to talk today, and Jessica's here, I hope she can hear me, on how past climates can inform our future. So can you hear me, Jessica?
Yes, I can. Can everybody hear me?
Yes, we can. So take it away, Jessica.
Great. Thank you so much for having me here. So I'll just share my screen and bring those slides up. Okay. Looks good. So I think my talk is a lot more broad and sort of, in scope than what we've been hearing about so far. We've talked in somewhat detail about tree rings, and which is one of the physical archives we have of past climates. But what I'm going to talk about is actually why we're even bothering to look at ancient climates in the first place. And of course, one of the motivations for doing that is because these ancient climate states inform us about where we're headed in the future. So this talk is inspired by a review paper that a group of us wrote 2 years ago now in Science that sort of outlines the many ways that the geological record of past climate can inform future predictions of climate change. And this sort of highlight figure here, actually these colors are scaled with global temperature change just to show kind of the continuum of cold and warm climates that exist in the geological record on the top, and also the continuum of future climate scenarios on the bottom, which range from pretty much staying at a climate that's similar to the one that we have today, to a middle road warming scenario that's more like the climate of 3 or 5 million years ago, to the high emission scenarios that move us into a very warm climate that we have to go deep into Earth's past to get sort of information about. So, put simply, as humans, we've begun this journey towards the high CO2 future by emitting fossil fuels. And since 1960, we've raised carbon dioxide levels by about 100 parts per million, which is a lot. And that's illustrated here by the Mauna Loa carbon dioxide record, which is our sort of physical and instrumental record of CO2 changes since the mid 20th century. And alongside this increase in CO2, we've seen a very linear increase in global temperatures since also about 1960. And if we normalize that back to pre-industrial time, all told, humans have warmed the climate by about 1.2 degrees Celsius, which doesn't sound like a whole lot, 1.2, but it is a lot. And we are really starting to see the impact of that warming on the patterns of weather and climate globally. And for me, actually, I think the summer of 2021 was a summer where a lot of this really hit home. In the US and also in Europe, there were a series of really extreme events that occurred, weather climate events, that I think kind of woke everybody up to, this is happening right now in my own backyard. Like, I am now experiencing climate change in a very personal way. And so just as some examples of those events that occurred in the United States, we had a really intense heat wave in the Pacific Northwest early in the summer of 2021. We had another record-breaking season of wildfires in California that burned many, many acres. And the uptick in wildfires has been linked to increased drought conditions in California, which is ultimately linked to human emissions. And less talked about maybe, but in the middle of the country, in the towards the eastern seaboard, they also experienced some extreme events. For example, like Tennessee had a record-breaking flood in the middle of the summer, of the likes of which they don't have an analog in the recent historical record. And when the IPCC report came out, the Working Group 1 report came out right at the end of the summer of 2021. And I feel like one of the statements that, a strong statement and a statement that's new when you look back at the older reports is this one, which is that it's indisputable that human activities are making extreme climate events more frequent and severe. And that's strong words from an organization that tends to be conservative about statements of climate change because they want to make sure that they're really well validated. I was an author on this report, but still this statement really struck me as like, wow, like we know that humans are linked to extreme events. That was not the case in 2013, and it is the case now, and that human-caused global warming is causing these extreme climate events to be more severe, and this is affecting us right now. So when we look forward into the future, of course, where are we headed and what should we expect? We would all like to know that. And climate models are our main tool, obviously, for looking into the future to give us an idea of what might happen. But at the same time, as we look into the future, and we're already at 400 parts per million, we're in CO2 levels that are way outside of the historical record. So if you try and understand climate change present and future by just looking at the historical record of climate or the observational record of climate in the last few decades or the last century, it's like trying to understand a new game by just watching a few plays. So if you just watch a few plays from an American football game, for example, you probably don't know what's going on or what the rules are. You need to see many games, many different plays to really understand how the game is played and all the different scenarios that can play out. And similarly, we need to in order to understand climate change, we have to go beyond the observational record because it doesn't have the kind of variability that we are going to see in a high CO2 climate. And that's why we need paleoclimate. So there are many different natural archives that record climate changes, and we've just heard in detail about tree rings. There are other physical archives that you may be familiar with, like ice cores or sediment cores from the deep ocean, corals and speleothems or stalagmites from caves. These are all layered archives that preserve climatic changes back through time in different ways. And, so what is the value of these ancient climate records? At a minimum, paleoclimate is about context, right? It's about placing where we are now in a deeper context of geology, of the sort of long-term climatic changes. And, probably one of the best examples of this comes from the ice cores. So the ice cores are special because they have these bubbles in them and they're preserving ancient air. So these bubbles come from when the snow turns to firn and then ice and then captures bubbles of the atmosphere at the time, and those are preserved in the ice cores. So we're basically, by analyzing the chemistry of those bubbles, we're traveling back in time and learning about what the ancient atmosphere was like. So we can directly measure carbon dioxide and methane back through time using the ice cores. And so the ice cores, first of all, allow us to extend that Mauna Loa record of CO2 back before 1960. And they tell us what pre-industrial CO2 levels were, right? So here's that same curve I showed you before. In the solid dots is the Mauna Loa curve now averaged over the annual cycle. And then those open dots are the ice cores going back through time. So it takes us back to the 1700s and tells us that pre-industrial CO2 was 280 parts per million. So now being at 410, 415, you can really start to understand how unusual that is. And of course, the ice cores take us back much, much further than that. They go back almost 1 million years. And when we look at that very long record of carbon dioxide, we can really see what humans have done is extremely unusual and completely outside of the range of Pleistocene climate. And so here, the CO2 record from the ice cores, you see the up and down of the ice age cycles back through time. And then at the very end of this curve, this very, very fast increase to over 400 that is human-caused climate change. So there's a lot of meaning in this context scientifically, but also sort of like as humans to understand what we've done. This is not all that paleoclimates can do, obviously. Paleoclimates are useful in a lot of different ways. And some of the sort of big four of what these ancient climates can do for me are here. So first of all, past climates can actually help us constrain key metrics of the climate system, like equilibrium climate sensitivity, which I'll talk about in a second, they can directly help us improve climate models because we can use past climates to test whether a model can actually perform well outside of the historical period, which is really important because climate models are calibrated to historical observations, but we're not in historical climate, so they need to be tested outside of that calibration range, so to speak. You can do that with paleoclimates. And of course, there's deep value in revealing the patterns of temperature and precipitation change, the spatial patterns. Again, climate models may or may not get those spatial patterns right. So having the ability to reconstruct fields of climate change in the past is really valuable. And finally, the Palaeclimate Record sometimes yields surprises, cases of climate change that you didn't expect and don't actually exist in the historical climate, but do exist in altered climates, both colder and warmer. So I don't have time to talk about examples of all of these. I'll just touch a little bit on climate sensitivity and sort of the patterns of climate change and what we can get from the Palaeclimate Record from that perspective. So just as sort of a background to this metric, equilibrium climate sensitivity, this is a metric that describes how sensitive the Earth is to climate change, essentially. And its technical definition is the global temperature response to doubling of CO2 concentrations, including the short-term feedback. So this is measured, it's an emergent property in climate models, and it's measured in a model by basically doubling CO2 or sometimes quadrupling CO2 and letting the model come into equilibrium and then measuring the global temperature response. And so it's typically, you'll see it displayed in these probability distributions, sort of like this, usually a skewed distribution with a long tail. And these are kind of typical values for climate sensitivity. The latest IPCC report puts that range between 2 and 5. So 2 degrees Celsius per doubling up to 5. And so, just to sort of some history, the estimates of climate sensitivity from the previous IPCC report that came out in 2013 are on the far left here. And you can see that the range was actually pretty large, with the box going from 1.5 to 4.5, and then those tails going between 1 and 6. And then the models that went into that previous IPCC assessment are somewhere between 2 and 5, the CMET5 models. And then the latest generation of models that are used that were used for the IPCC AR6 report, you can see that red box is now edging up. And a lot of these newer models are quite sensitive, including in the US, our flagship models from NCAR and GFDL, and some of them have climate sensitivity that's over 5. And so there's a lot of reasons for that. And we understand that, some of the basic reasons for that, which has to do with cloud and aerosol parameterization. But the question is that right? Like, is climate sensitivity actually much higher than we think? Because that's kind of what we're getting from these latest rounds of models. Of course, it's quite important because if you compare end of century predictions of global temperature between a low ECS climate model and a high one, they can differ dramatically. So this is just an example using 2 generations of CNRM, a model from France. Their older model has lower ECS. And so this is under the high emissions scenario. It would predict about 4 degrees Celsius of warming by the end of the century, whereas the high ECS model is 6, right? So that's a 2-degree difference. We would like to know whether what climate sensitivity is with more precision so that we can narrow these projections. And paleoclimate can do that for us because we have this huge range of climatic changes in Earth history, including extremely warm climates, where we can investigate climate sensitivity and really see if we can get a better idea of whether whether these models, what their sensitivity means if we take them back in time. So this is a summary figure again from our review paper, just showing the trajectory of global mean temperature for 100 million years. So we're really zooming out here on the geological level. Our best estimates of CO2, which are still quite uncertain when we move beyond the ice core record. It is difficult to reconstruct CO2, although there are ways that we can do it. But broadly speaking, the climate has been cooling, generally since the mid-Cretaceous 100 million years ago, and CO2 has been declining. And so we have this whole menu of warm climate states, the mid-Cretaceous, the Eocene, the Pliocene, that represent different CO2 levels and different temperatures and different climatic behaviors. And so for context, our future projections are there on the right, just showing, you know, low, medium, and high emission scenarios in CO2 space. So as an example of how we can look at climate sensitivity and other metrics of the Earth system from the past, I'll focus on the warm Eocene period 50 million years ago, which is what we call a greenhouse climate. We know that the climate was really warm at this time. The CO2 levels were around 1,000 parts per million, so we're way higher than today. There were no large ice sheets in the poles, and things were quite steamy. We have a number of interesting paleoclimate proxies that tell us about the temperature and precipitation and biosphere of this ancient warm world. But perhaps one of the simplest and kind of coolest pieces of evidence that was really hot is just the fact that we find tons of crocodile fossils in the Arctic, a place today, obviously, crocodiles don't live, and crocodiles are cold-blooded. So they really need to be in a place that's fairly warm. This is sort of like your biological range of crocodiles. They like it to be above 20 C. So just by that, we know that especially the polar regions were extremely warm in the Eocene. And of course, we can ask climate models to simulate this ancient climate of the Eocene. And sure enough, they kind of show that there's this really extreme level of polar amplification during the Eocene. And you can see that here with a big map. That's a climate model simulation of Eocene temperature compared to pre-industrial conditions. So extremely warm poles in line with the evidence for crocodiles, warmer on land than the ocean. And overall, you know, this is actually very similar to what we see, for example, in the future simulations of climate change at the end of the century. Here in the upper left-hand corner is a plot from the IPCC report just showing the simulated change at 4C warming. The magnitude is not as extreme as the Eocene, but polar amplification is also a feature of warming. So going back to my point about how past climates can inform patterns of climate change, even in cases like this, where the continents have moved around, it's still quite useful. And same thing for precipitation. The basic patterns of precipitation change in these warm climates of a wetter tropics, wetter high latitudes are remarkably similar to our projections for the future. So there's a lot to mine there in terms of understanding the patterns of temperature and precipitation change. Back to the climate sensitivity point, what the Eocene gives us is a paleoclimate target. So we know from our proxy evidence roughly what the temperature and the CO2 levels were. And that's that square here. And you can see that it's pretty broad in CO2, right? Like that's a hard thing for us to estimate, but nonetheless, we do have bounds on what the CO2 could have been. Likewise, we have bounds on what the global mean surface temperature could have been. And what we can do is ask different models to hit that target. So can you hit that target? And how does that relate to a model's climate sensitivity? So my colleague Zheng Zhu did this experiment with 3 generations of the NCAR model. The oldest generation of the model has a low climate sensitivity of about 3 degrees per doubling of CO2. And you can see that when we turn up the CO2 and try and simulate the Eocene, it misses the target. It can only produce that level of temperature at very, very high levels of CO2. So perhaps this model is not sensitive enough. Conversely, if we use the latest generation of the Community Earth System model, version 2, it has a very high climate sensitivity of about 5, and it also misses the target because it gets really hot even with a smaller change in CO2. And so this is obviously a Goldilocks game, and then the model that really hits the target is the CESM1 version of the model, which has that middle climate sensitivity of 4. So here is just a simple example of how we can use the paleoclimate target to test which version of the model can perform best when we put it up against a warm climate, the task of simulating a warm climate. And we might conclude that the latest generation of the model that has that really high observational climate sensitivity of 5 is perhaps too sensitive. Okay, we can also learn a lot from, beyond these sort of mean state in climate that we get from paleoclimates. We can also learn a lot by studying what we call aberrations. So sudden and rapid changes in climate away from the base state. And if we're looking again at the Eocene, right before that sort of peak warmth 50 million years ago, there are a number of these aberrations that are called hyperthermals, these really rapid global warming events. And the most famous of those has a name. It's the Paleocene-Eocene thermal maximum, a mouthful, or PTM for short. And this event is an ancient global warming event that was probably caused by volcanic emissions. And so we know that CO2 very rapidly increased from the baseline of 1,000 to about 2,000 parts per million. The global temperatures spiked at the same time by about 5 degrees Celsius. And also that we see this very dramatic reduction in ocean chalk. What do I mean by ocean chalk is basically the calcium carbonate ooze that's in sediments that builds up at the bottom of the ocean, and it's made of these thousands of these little tiny shells, the foraminifera shells, and they make this ooze. And it's actually one of Earth's great CO2 buffers. Ultimately, this chalk actually serves a purpose in the climate system of neutralizing CO2 when it enters into the ocean. And this chalk disappeared during the PTM. And you can actually see this happen in sediment cores recovered from this event. So you can really see this climate event just visually with your eyes when you look at a core, it's a sediment core of the PTM. You don't even really need any fancy proxies yet to see what's happening here, that before the event, the sediments have that sort of chalky flavor. Once you hit that global warming, there's an extremely sharp boundary, and all of that ocean chalk calcium carbonate dissolves. You're left with that red pelagic clay. And 10,000 years later, same thing. Obviously, it takes a while for the Earth to respond to that CO2 perturbation and start to process it. Eventually, the CO2 is buffered and you see a return of the chalky sediments, but not until 100,000 years later. And this is a type case of how the Earth system processes an extreme version of CO2, like the one that we're doing right now. It takes tens to hundreds of thousands of years to recover from a CO2 aberration. And just to sort of juxtapose the PTM to the future, it's kind of amazing to me that the higher emission scenarios actually show ocean pH dropping to the same, if not more extreme levels than what we think happened during the PTM. We estimated ocean pH drop in the PTM that dissolved the calcium carbonate is about 0.3 pH units, and we could get there by 2100. So even though this event occurred millions of years ago, ocean acidification is pretty fast, right? And that's one of the things that we can learn from by studying the dynamics of ocean acidification, for example, during an event aberration like the PTM. Now, I just want to close by saying a few things about water and what the Palaeoclimate Record has to offer about water. So I live in the desert, so water is incredibly important, right? We're always worried about running out, and we are running out. Long story short, in California in the Southwest, where we're currently sitting in what is now the worst mega drought in the last 1,200 years, which we know thanks to the long tree-ring record of drought here in the Southwest. But it's still very beyond sort of the last few thousand years. It's actually very difficult to reconstruct the water cycle from paleoclimate. Nonetheless, I think that there's a space to do that. And I just want to return to this, what the IPCC report has said about climate extremes, that basically every increment of global warming, the frequency and intensity of extreme events increases. So the likelihood of an extreme event increases and the intensity of that event increases. And I guess my question to throw out is, how can we benchmark the increase in extremes of the Palaeclimate Record? It's a hard question. Interestingly enough, there are archives of extremes in paleoclimate archives, like even the sediments. And just as an example, this is a massive alluvial fan deposit that all got laid down during the PTM event in the Pyrenees. And there's a person there at the bottom of the screen for scale and a scale bar. And this whole sequence of sands was all dumped out during the PTM. And it's thought to represent a series of flood events that occurred during that climate aberration. So just as we might expect, obviously climate extremes were probably pretty intense during that ancient global warming event. Can we use the geological record of extremes in tandem with climate models to understand this with more detail? I think we can, and that's actually a project that we're starting, which is what I call paleoweather. So the idea of trying to extract weather statistics out of past climates. This really brings past climates on the same playing field as as the future because we're looking at the statistics of extreme events. So we have to start by doing that in climate models. In order to look at the statistics of floods, hurricanes, and things like that, we need model simulations at higher resolution than we typically do for paleoclimate. So we've just been approved to do some of the highest resolution paleoclimate simulations to date with 1/4 degree atmosphere, 0.1 degree ocean, with water isotope tracers for 3 key periods of ancient climate, the last glacial maximum, the Pliocene, and that Eocene warm period that I'm talked about. So those are going to be done next year on the new NCAR supercomputer Derecho. And this will give us sort of a first glimpse of the statistics of extremes as the model sees them. Of course, we need to benchmark that with the paleoclimate data, and we have some ideas about how to do that. So with that, I'll just say thanks for having me here virtually to talk to you, and I'd be happy to take some questions.
Okay, thank you, Jessica. So do we have some questions in the audience first? Okay, online? Go ahead.
So a question from Paulo Ceppi. How do you account for slow feedbacks, ice sheets, dust, etc., when estimating ECS from paleo data?
Yeah, so in the latest, sorry, I'm getting a little feedback from the room, but in the latest IPCC report, it actually includes, they measure ECS, including everything, including land surface and dust feedbacks. And the only thing that's not included in the metrics of ECS are the ice sheets. So yes, we do need to separate out the radiative effect that ice sheets would have. So we don't have to worry about that in a warm climate like the Eocene because there are no ice sheets. So we're good. But when we look at, for example, climate sensitivity of the last glacial period, we do need to account for the fact that the presence of the large ice sheets over North America and Europe does have a really strong radiative impact. And so we do need to separate that impact out in order to look at a climate sensitivity that's similar to the way we measure climate sensitivity in the observational record. Alternatively, some people prefer not to split anything out and just measure what we call Earth system sensitivity, which does include those very, very, very long feedbacks, such as the ice sheets.
Okay, Jessica, I have a question now for you. With the modern climate models, we know where the continents are and everything, but we still have to put fixes into models like the Indonesian through flow because it's so small compared to the scales. I just wondered how confident we can be when you're in the Eocene. You might have some of those that we're not aware of in terms of the positions of the continents, and some extra flow of water is needed. But how do we know that?
Yeah, I mean, we don't perfectly know the continental configurations, right? That's also based on geological reconstructions. So when it comes to looking at, a particular, hyper-regional situation, yeah, there's a lot of uncertainties about that. But what I would argue is when you're talking about the big patterns of climate change, like polar amplification, like the monsoons, these sort of supra-regional patterns, it doesn't really, I mean, of course, the continents, focus the monsoons in one place or the other, but the climate dynamics are the same. So, if you kind of look broader scale, right, you can still learn about these broad scale patterns of climate change from ancient climates, even if we don't know exactly where the continents are. You just have to be aware of how the continents might steer and change regional climates in a very different way in the past. And that isn't, of course, not analogous to present day, but the large scale patterns are robust and kind of persist. At least I would say, for the last 100 million years, when you start to get into, supercontinents and things like that, it does sort of change things. Although you still have, the tropics, the subtropics, and the poles doing dynamical things that are useful for present and future climate change.
Thanks. We have one more online question come in late.
So this question is from Robert Nichols. What is your feeling about ocean acidification as a key threshold on future climate change? Your talk gave me the impression it is being underrated.
It is definitely, a major issue, and, like, it's fast, right? So we are already the oceans have acidified. So how acid they get really depends heavily on the emissions. And you can see that actually the future predictions of acidification range from basically stopping it where it is now at the low emission scenarios to really acidifying the ocean, right? Because it's just such a big difference in CO2 levels. So it's not so much of a threshold though, but as differing degrees. And we have to make a choice. If we're going to emit a lot, we're going to see a lot of damage in the ocean. I do want to comment on that word threshold, because I think that is there is a misconception that there's some sort of cliff out there that we're just going to kind of like fall off of, and then the world, just everything gets messed up, right? And that's not really how it works. I mean, things are still incremental. And so when we look at where we end up at 2100, it's incremental. We either are, holding ocean at this pH, or we're acidifying it, and everything in between is also possible. And so I always say, don't obsess about whether we make 1.5 or 2 degrees. Like, there's nothing at 2 degrees that's particularly special about crossing that threshold. It's just that things get incrementally worse the more that we emit. And I just mentioned that because I know there's like a lot of anxiety about crossing those thresholds and what would happen. We'll be okay, but things are worse the more you emit. That's a simple thing.
Okay, thank you, Jessica.